Okay, yeah, great. Yeah, as Henry is not here, maybe he will introduce his basic features of both the histogram and UHI later when he come in. Both the histogram development is very active. Currently, we are still contributing to it. For example, one of the most important features that we want to achieve is numberification. Number is a high performance. Number is a high performance Python compiler that uses the industry standard LLVM to allow a fully number enabled event loop for analysis. Histogramming steps need to be implemented with number decorator. In this summer, we will investigate the ways to enable both the histograms field from inside the LLVM number loop without stepping through Python. We were able to make a faster event loop, thereby improving the performance of our projects that rely on both the histogram. And here is the pseudocode. Currently, we can achieve this. As you can see, the field is outside the number function. Our goal is to make this work. That is to make the hist field within the number function. Powered by both the histogram, a library of histogramming for analysis named Hist comes out. Hist library provides useful shortcuts for plotting and profiles, including the following features. To participate, you can run the notebook via the binder link on top of this. Hist allows names for both the histogram axes. The names are unique identifier in a histogram, which are used to support useful features, such as field and project. Especially, Hist design named Hist to provide name shortcuts for the histograms that contain name axes. For example, here we can initialize some Hist axis and use it to construct a histogram. As you can see, you can obtain the axis names and labels from the histogram. Hist allow named field by name based on the normal field of both the histogram, which is much safer and more readable. Hist has customized wrappers when displaying a Jupyter notebook and supports dark mode. For example, here is a 1D histogram, and here is a 2D histogram, and here is 3D. Besides the fancy wrapper, the users can explicitly obtain the data by plot and show method. Let's try an example. Here we can try show. This is a histoprint, and we can also use a plot. Yeah, this is use matplotlib plot. Okay. Hist uniform histogram indexing extends both the histograms UHI and provides high energy physics users with handy accessing shortcuts. For example, to access the central element of the 2D histogram, we can do the following things. Note that this is supported by both the histogram and Hist, but these accessing methods are only for Hist. Besides, Hist UHI also supports rebeam for histograms with the complex number shortcut. For example, here is the original 2D histograms, and we can rebeam it. As you can see, the beans are much wilder. Besides the standard construction method of both the histogram, Hist provides quick construction for users. Both the histograms construction looks like this. But here we can use the new operator to quick construct the histograms. And fill it and wrap it. Histstack is a newly development features in the latest version of Hist. A Histstack holds multiple histograms into a stack whose axes are required to be matched. Here we can create a stack using the named hist and named hist copy. As you can see, this is the named hist and this is named hist copy. To demonstrate that the axes are required to be matched, let's change the project axis to another. Yeah, you can see the histogram axes don't match. And by passing into a hist type argument, you can get the field histograms. One of the interesting example of stack is you can create a stack using by converting the histograms with string category access. For example, here you can create a 2D histograms with one axis regular and one string category axis. Here you can create the stack with two histograms. One named good and one named bad. Let's see. Here it is. Yeah, you can also get the field stack and field plot and the reversed plot. And you can get the histogram inside the stack. Hist allow users to read dictionaries or panda data frame directly into Hist. Here I use a data set and show the pie plot of the histogram of a CSV field. Yeah, here is the pie plot. There are some other interesting shortcuts of Hist. For example, we can get the density of an existing histogram via density method. We can get the profiles of histograms with respect to y-axis. If you want to know more about Hist library, welcome to our GitHub repo. Then let me pass my mic to my collaborator, Henry or Aman, to talk about Hist plans and boost-histograms current status.
Okay, thank you. Sorry about that earlier. My audio was off, so we're just sitting there wondering what was happening. Okay, I will share my screen. Okay, and I will make that a little bit larger. All right, so I'll give you a little overview of sort of what happened in the mostly since the last PyHEP for boost histogram and the development of UHI. So just start here. So boost histogram 1.0 came out and it had some great features. One of the best features was the removal of Python 2.7 and 3.5 support, which means the other features, including easier subclassing and full static typing across the entire library, were actually obtainable with fewer lines of code than the 0.13 release. And then along with those things, quite a few features that were intended for 1.0 were also backported to the Python 2 branch, which included this simpler Pythonic metadata system. So you can now just set any attribute on a histogram or on an axis, and they just get passed along. It behaves as if they were just regular nice Python classes, but it happens to move them through the C++ computations as well. It gives you better access to the accumulator storages. So there's really easy ways to get access to those sorts of things like the values and variances without having to change what you're doing based on what kind of histogram storage you have. And of course, the Plottable protocol, which we'll talk about a bit later. And there were lots of updates to various other tools that happened as part of the Boost Histogram work. PyBind 11 and CI Build Wheel both received major updates as part of this push. The PyBind 11 and 2.6 has new CMake and setup tools helpers that were heavily based on the Boost Histogram setup tools and CMake tooling. There's faster accumulation. So if you're writing accumulation in PyBind 11, it's 40% faster, and that was to help Boost Histogram. We're pushing for Python 3.9 support, Universal 2 support for the new Apple Silicon, including 3.8. Boost Histogram had to support that, and much more. Let's take a little look at what a statically typed histogram gives you. So I'm just going to write a very simple little script here. I'm just going to import Boost Histogram. I'm going to set up a single one-dimensional axis. I'm going to go ahead and just grab some values from that. And then I'm just going to go ahead and run the reveal locals command, which is a mypy command that will just show you what the current types of everything are. So we'll do that. And you'll see that the revealed types were H is a histogram and vals is a numpy. So it understood that this thing was returning a numpy, right? And you see the new numpy 1.21 things there. We don't really do anything except any there yet. If I turn that off, it would then give me a pretty little green, no issues. Okay, so now let's try a couple of common mistakes. So one common mistake would be what if you accidentally did an int category here, for example, and forgot that you changed that. Well, MyPy will find that before you even run your code and tell you, hey, these things need to be integers because you're asking for an integer category here. Or for example, you could make a mistake in indexing and pass something that's not valid there. Boost Histogram doesn't support strings in indexing, and you get an error. And in fact, since I didn't actually change this back correctly, you'll notice one of the benefits of this over tests. For one, I didn't have to write any tests, and two, I'm getting both errors, even though these are not in separate test cases. So normally you should be writing lots and lots of test cases because you only get one error per case, and then it just quits. But here I'm seeing all of the errors at the same time. Just to keep from writing too much, I'm going to go ahead and switch that back. And another example is you could misspell something. I saw somebody put as one of the most common errors they make, they mistype something. Well, MyPy is definitely really good at catching that. If it's statically typed code, it will tell you. In fact, it'll even suggest the correct thing if it's a close miss. So several of these things. So a lot of the common errors listed on that page were actually things that MyPy can catch very easily. So if you're using it, this will be much, this will sort of help you use it better before you actually have to write code. And there you go, back to no errors. All right, let's take a look at Boost Histogram 1.1. This was released yesterday and adds a few exciting features. For one, it finally added the Python 3.8 Apple Silicon support that was missing for quite a while, but the very last official release of Python 3.8, the last feature release, actually added support for this, so we were able to add it kind of just under the wire. And then scaling and addition now affect the flow bins too. So that's when you do the scaling or addition shortcut where you just multiply by a scalar. But sort of the big thing in there was this new experimental support for selections of category axes. So I'm just going to import boost histogram into my notebook, because before I had it in my little script that I wrote out here. And then I'm going to make a new histogram that has this good, bad, and ugly. First time that you use this, you'll get a little warning saying that this is experimental and that removed bins are not being added to the overflow, but that may change. But you can see that I was able to pass a list in here and get just the 0th and the 2nd item from that. So this gives me the ability to reorder axes. Now I could put in a different list, a different ordering here, and we get a different ordering out. This also lets you select by names. Now, since you've already seen histogram, because I'm going second, I'm just going to try this with hist as well. So I'm going to import hist. I'm just going to go ahead and convert H to a hist because they're the same thing. So, oops, hist. Okay, and there you go. Now we have a hist. This works the same way, though actually in this particular case, we should probably print it so that we can, oh no, it's right here. I'll just look right there. So you can see we're doing the same thing. We still get the warning, but the warning is already, it only shows once. So, and in hist, we don't have to add these looks because it's obviously a string. There is no ambiguity there. So in hist, you can just, verbally putting the right number of brackets, you can just do that. And now I get bad, good, I get exactly this out. See the axes. You see, I get exactly this out. That good when I do that. So this just works here. If this was an integer axis, you can only do this on categories. But if this was an integer axis, let's do say something that's obviously not indexes, then this is still selection by position. And if you want to select by the values in it, then you use the J shortcut, just like you saw before. So 3J, 5J, we pick out the 3 and the 5 values. So that just works as well. Okay, so one of the other big changes that has happened is the addition of the UHI, the Unified Histogram Interface. And this is a statically typed protocol that allows you to plot histograms from any source. So this is supported by boost-histogram, it's supported by Hist, obviously, because this just adds to boost-histogram. It's supported by uproot 4, it's supported by PyHEP, it's supported by Histoprint. So, and hopefully there'll be more libraries here as well. Any of these libraries can plot anything from one of these other libraries without depending on each other. So you can just hand an uproot histogram directly to PyHEP or Histoprint or anything else that supports UHI. And that will just plot our work without having to convert it to a boost-histogram or a hist or anything else. Okay. And there is actually a PyPy library, PyPI library for this, and it has some helper functions and things. You don't have to depend on this at runtime at all, but if you'd like to, there are some nice handy features that are in the library. So feel free to check that out. But this is what this protocol looks like. So this is just a overview of the things that you're allowed to use. So you get a series of methods and a property here that you can use to get information about the histogram and 2 properties. Values, variances, and counts are the value, variance. I think we need somebody to unmute or to mute. If, admin could do that, please. Okay, so values, variances, and kinds. So this is the value, this is the variance in whatever that value is, and this is the counts, which is how many fills have been received or ineffective fills for weighted histograms. And then the kind tells you either count or mean, And then the axes is a sequence of axes. So you can index it and loop over it and stuff. Axes themselves have their own protocol, and they have a they can be indexed, and if they're indexed, they either return a tuple of upper lower bin, or sorry, lower upper bin, or they just return a discrete bin value, so integer or string, and that is always the same for the axes, for an individual axis. They support a length, they support iteration, which gives you the obvious thing from those two things. And then they have a traits property, which has has circular and discrete. So it has at least those two things. Okay. And then if you use it, it's statically verified by MyPy. So if you just say, hey, I take one of these plottable histograms, then it will verify that you actually only use those things, the things I just showed you. If you want to write your own library, and so say like Uproot or Boost Histogram or some new library, and you want to make it support this protocol, then this is what you would do at static type check time. You would get this, it's actually Plottable Histogram, not Plottable protocol. You would just import like this, and then, oops, sorry, I jumped. And then you could just you could say, well, only if you're type checking, or if this file could just be a type check file only, then just take some value, doesn't matter what it is, but it's going to be a plottable histogram, and then you can just cast your histogram none to your histogram. So this wouldn't work at runtime, doesn't make any sense. This would just be none, but it doesn't matter that this is none, because what this is doing at type check time is it's checking, I have an instance of some sort of my histogram, and is it a plottable histogram? So that's what it does at type check time. So this will fail a type check if you didn't fill in all of the necessary bits and pieces. So this is how some of the other libraries are able to verify they really are plottable histograms. Okay, so let's take a look at this in action. So let's do a little plot of just some random numbers, and then we'll also try a little 2D demo. Okay, so I'm just going to set up some initial libraries here. I'm going to create a random number generator from NumPy 1.17 or so, whenever they switch to this method. And then I'm going to go ahead and create a histogram. I'm going to go ahead and make sure we import hist here as well. Yep. And then I'm going to go ahead and take a histogram, and I'm going to fill it. And just to be fast, I'm going to fill it in 4 threads. And then I'm going to hand this to MPL-HEP. MPL-HEP doesn't know anything about boost histograms or hists, but it knows how to plot a plottable histogram, and this is one. So this is a plot. You'll see the correct values down here. I can actually change this to hist. Probably spelling correctly. And it can plot that as well. A few of these libraries have some optional support for picking up names, but because Boost Histogram doesn't support named axes, it couldn't be added to the protocol. So, but some libraries can check and just add a name if they see it. So there we go. We were able to plot that. We can also pass these to Histoprint. So if I pass this to Histoprint, .print hist, again, doesn't know anything about this library, but it knows how to detect and plot a plottable histogram. And let's just try a 2-dimensional demo of this. And you'll see a little bit of rebinning here. And since I switched to hist, I can actually switch to the hist binning and make that a whole lot easier to read, because there's so many extra characters there, including parentheses. I don't like parentheses. Okay, and then that's the exact same thing, but this time you can now actually read exactly what I'm doing up here instead of having lots of extra characters. All right, and then we can try a two-dimensional demo. We'll just open this image and turn this into a NumPy array. And then again, grab a random set of random numbers. We're going to throw those. We're basically going to do a probability of whether they hit this image or not. So this is a way of turning this into a list of tracks, and these tracks are things that either hit or didn't hit this, and they tend to get deleted if they didn't get hit this using this probability. So we're going to go ahead and fill this. We've seen Hist now, so we can do this in Hist. Hist. And we can go ahead and switch this over so that we can get access to our names. Okay. Try to change too much there. There we go. So we can go ahead and import and fill that. And then I can go ahead and this is actually based on an older. Actually, I'm going to do h.plot here. There we go. So there you see the plot. And you could manually plot this if you wanted to, but that's, I can go ahead and show that. And this is just building our own little plotting function out of raw matplotlib primitives. And you can even rebin this or zoom into a specific spot. And the nice thing here is you can actually just read these coordinates off these axes and just plug them in here and just stick J's on the end. So from X, it starts at 0.2. From Y, it starts at 0.8, or it ends at 0.68, sorry, on X. Then at Y, it looks like it starts around 0.5 and ends around 0.8. Again, and you just can read that off of the histogram up here, and then you can get the zoomed in version down here. So this is really great for making cuts and looking at things, balance analyses, various things like that, where you might want to look at a specific subset. You can also, of course, sum across this. So, for example, do a vertical sum there, and then I'm using this weird plot thing that's only plotting 2D stuff. And then if you don't add star, you can take a look at what the profile would look like across. And again, I just take a look. Okay, so let's switch over to Aman, and then we'll have some tutorial materials to look at.
Hi, I hope I'm audible.
And do you want to share your screen, or do you want me to just keep sharing?
I'll just share my screen. So yeah, I hope the screen is visible. We're going to talk about the future plans of it and like the current features as Nino discussed we've added. So what we have a lot of features currently coming up, which also integrate with the Scikit-HEP and various other libraries. So let's get the overview. First, we're planning on introducing an interpolator. So it would be a class which could interpolate over histograms, and that has a statistical advantage. And it could take the histogram and return the interpolated values. And we can have various interfaces for the kind of interpolation we want. For example, we can have a hist.inter. For example, if the class is .inter, we can just run that, and we can call a linear interpolator, and it would do a linear interpolation on the histogram that we have passed. And similarly, we could do that for cubic interpolation. So what the basic plan is that first we introduce the basic ones, the standard interpolations, and then we can also give support to the users to make their own based on different parameters. So it would help in better estimation and interpretation of the data. Then another feature that we want to add from the COFFIA library would be the plot grid feature. It would help in creating a grid of plots. And after that, we can also look into arbitrary rebinning. So the current issue with rebinning is that it requires a lot of preconditions to work on. So suppose we have arbitrary rebinning and suppose we have a very large histogram, which are inherently difficult to work with. Almost all libraries, like very few libraries support histograms with large bins. So if you have a lot of bins, what we can do is we can arbitrarily rebin it. Suppose we match the edges on upon a function, and then we have the new bins which can be plotted faster. So that basically improves the efficiency of the plot. And then we also plan fills from awkward arrays, as Jim presented yesterday. So we could take in awkward arrays, and the fill function would take it in intelligently, and then we can use the various features that are provided in awkward arrays, ak.flatten, ak.fields, and ak.unzip, to sort through the data, and depending on the different kinds of data, we can fill those. Another feature would be statistical functions. So we have functions in root and in other libraries which can be added to Hist, and those could be used to handle efficiency histograms, and again it would help in statistical analysis. So it would compute the calculation of efficiencies and their uncertainties. That is another feature that we have planned. And other minor features would be improved reps. As Nino discussed, reps, we have the different representations of the histograms that we define in the Jupyter notebook itself. So if we have histograms with various axes and multiple information, we would like to cut through that information using certain commands. So when we have better details and we can have configurable options, which give us a better output. So suppose we want just a specific part of the rep, we can get that. And we're also planning to integrate the Hist package library with fitters. So that would ensure that it interacts properly with various libraries and fitters such as zfit, PyHEP, and goofit. And another thing, we're dropping Python 3.6 support. So we made just a release was made just a few hours ago, and that was the last release with Python 3.6. And our development branch would soon drop 3.6, and then onwards we'll support 3.6, 3.7, and above. So that's what we have planned in Hist, and now Henry would dive into what we've discussed, and we can get in the tutorial and see how to use histogramming features that we have discussed today. Thank you.
Okay, I'm just going to share this again. Okay. So hopefully at this point you're either running locally or you tried out the binder, so you'll have something to run. But let's take sort of a more in-depth look into some things that we can do. So the first one, we'll just sort of glance over this first tutorial. This was sort of a high-level introduction, and it was originally targeted at a bit broader audience, but it gives you a sort of very gentle introduction into histogramming, sort of assuming that you know NumPy, and then moving over to histograms. So let's just run a little bit of it. There's a couple of useful things of there. I'm not going to talk through all the details here. So that's why you might want a histogram. And then, as we've already sort of pointed out, histograms are sliceable. You can slice them by either their bin indices, or you can slice them by the data coordinates. This is often easier if you're reading something off. You'll see these things are the same. You'll also notice that they are carrying a long flow. So they have flow bins, just like say a root histogram would. And you can rebin them really naturally. You can sum them up. I assume this audience does know why this is not the same number as the number of things we added. So I'll just do the answer here. So flow equals true, and that's actually the full number of bins. This is what it describes in here. So we'll not do that exercise. And then there are a variety of different properties. So you have an axis, basically something that looks like a tuple of axes. And then you can access centers, edges, widths, name, so various things like that. You can actually avoid this, this 0, and you'll just get back a tuple item, and this will actually be correct for multiple dimensions. So I should be able to just broadcast this together and use it if it's something like a centers or edges or widths. So that's quite powerful. And then you have values, variances, and counts. Counts and values may often be the same if you're not dealing with a mean storage. And variances may return none if it can't track it. So if it's not weighted, this may return none if it doesn't think it can track what the variance actually is. Depends on how you feel. And we can actually get a raw view of the data as well, which is for a regular set of doubles. This is really simple, but for other storages, there's more to this. And there's, as you've sort of seen, there's multiple ways to define these. We have this sort of the standard method, and then there's also a shortcut method that Hist adds. You can actually write this out now if you want. This was originally different so that to make sure that you wouldn't accidentally make a mistake and put this inside here. But actually you can do that now. Partially because now we have a new. So let's say if you made a mistake like that, it actually just still works. So that was the thing I was really worried about, that you would, these two things look similar, but now that works too. So you can use the full names if you don't like switching between the sort of the short names and the full names. This is nicer, and in fact, the tab completion will actually recommend this one now. Won't show you the other one, won't show you the short one. Okay, so that's just sort of a quick little overview of sort of the key bits of things that you'll need in order to play with anything. So this is an example with more dimensions. So let's try playing around with this histogram. You've seen how we did all the stuff in one dimension. Let's try playing around with this in 2 dimensions. So for example, if you want to just select out this piece, let's see a plot. Let's do h.plot. Now we get a little bit nicer units here. I'll just do that way. How would you look at just this piece? So try that for a minute. Use indexing expressions and try to select from -2 to 2, -2 to 2. So in this case, -2 to 2 in value space. This is just a one-line thing, so you should be able to just paste it into the Slido if you like, if anybody has an answer for that. And then I see we have questions, so I'll answer questions after that while people are playing with this a bit. So I'll answer some questions and give you a chance to just play around with indexing this. And there's a few suggestions there. The next thing I would try is look at profile over and y-axis. X. There's several, actually, a couple different ways to do that. And oh, S, not X, W. Because I see the units, I see the little labels up here. So try this next, and then I'll answer questions, and we'll come back to this. So it's not questions. There we go. So I'll start with the most highly voted, since Slido puts the ones that people are voting for. So if there's a question you have as well, just vote for the existing question, and they will come up to the top and be more likely to be answered. So for accumulator storages, our wider statistics like Poisson or asymmetric error is going to be supported. So right now we have just a set of three special storages. We have a profile, a weighted profile, and then we have a which is a mean, and we have the weighted sum. The issue with adding more of these is that if they require different calculations, you have to implement them in C++, which is really easy in boost-histogram C++ site. But then you have to add them to the library, which again is not particularly hard, but then it will make it larger and slower to compile and have issues with running out of memory and things if you get too many of these. So some things, yes. What we'll probably be trying to do on sort of very long term would be to add a way to adjust this by, say, having storages of different sizes and then passing in a C types pointer. Because we currently do this for transforms. So the answer for transforms, if you have a different transform that you want to transform a regular axis into something else, you can write anything you want, write it in, say, in numba and C types as a C callback, C func, and then just pass it in and it works. And it gives you about 10%, gets you to within about 10% of the performance of the raw C++. So there might be some way to do something similar with a general storage backend, and that would be a very valuable addition. Okay, how well does boost-histogram and Hist deal with competing stat errors in the bins? It should deal with those. You need to use a weighted histogram, but in that case, the statistic should be propagated through as when you're check dividing two histograms, but definitely most of the operations and fills and things would work there. I will verify. I think dividing two histograms works at some point. I think it had a bug originally. Will interpolation use bin centers or edges? I think that would have an option to customize it. There will be a general interpolator class that these things will be based on, and it'll have some structure. So it should be really easy to add your own interpolator when we'll provide some default ones like linear and stuff. So linear itself might not have an option in it. Depends on how easy that is, but it would be very easy to add interpolators that use either one. What is the best practice for converting PyRoot histograms? Something which can be plotted by matplotlib. Well, certainly you can just write, you can actually now just pass them in. So PyHEP uses UHI and the UHI library, as that provides really nice, handy ways to get some of these things. And the UHI library and its adapter actually supports PyRoot natively. It picks up, it detects if it's being passed something that's PyRoot, and it will convert it to a simple object that happens to exactly conform to the plottable protocol. And so the easiest way is really just hand it to PyHEP, and that will should just work out of the box. And it's because of the UHI helper functions. Things that do not use UHI right now, you would then have to just manually do that. Though I would actually really like to add direct UHI support to PyHEP. I think they might be willing to accept that as a Pythonization. So that's something I've intended to do for a while. Is all the information in the original input histograms in the stack accessible from the stack? Yes, they act just a lot like, well, they are a container. So in fact, something that I didn't realize worked until after we released, and then I did. I think it was in here. I was adding a stack. What was I doing? I was adding the stack true and his type fill just to see if that worked. And I didn't like the way that this one came out with this on top. So I thought, well, why don't I just try reversing the stack and plotting it, and it worked. And that was actually a last minute change in stack to add the fact that and if you pass in a tuple here and change the stack around, it still returns a stack. But you can always pass a stack to the stack constructor. So you could just say star and then whatever collection of histograms or even star stack, because it's iterable, and make these any way you want. So yes, there it just use bracket 0, and that's the original histogram. And it actually has a title as well. If it came from the dot stack constructor, which I assume is how most people will do it. I assume most people would probably create this axis beforehand, fill it, so then you get the performance benefit when you're filling, because you're only looping through this once. And then when you do this, the name for each one of these things, so good and bad, actually gets attached to the items in the stack. So if I do, I have to run all above selected cell. Okay, and then if I run this, and so if you take a look at this S, so that's the stack. If I just index in, those are the original histograms. I can even slice, and I get back a stack, which was the thing that caused that other trick to work. And if you look at one of these histograms, these actually have a name attribute that's been added, and that's the original cell value that it came from. If I were to do a stack over something that was not strings, I would get an integer or a pair of floats here, which is a little bit weird for a name, but it's still extremely useful for filling in labels and such. We're down to 1 vote question. So if anybody wants some of these, I would then either add some votes. I say add some votes, or we'll answer those later on Slack. Almost said stack. Okay, so let's go back to this example. So of course, the answer for plotting. The answer for plotting was simply just h minus 2i to 2 j, sorry, to 2j, and that's how you would get that one, except I have to do both because it's a 2D histogram version. 2j, and then dot plot just to see it, because I like this plot better. Honestly, this one's not too bad. It's not that many bins. And then for this example, there were 2 ways to do it. One would be if you want a profile. So what I asked was I wanted to integrate over the W axis and just look at the S axis. So there's 2 or 3 ways to do that. One would be to just use indexing expressions. So I could do well, I don't have to put the colons. I could do that, and that would give me just the S axis, what you see, because it's passing these names through. This is very helpful. And then it's summing over the other axis. This, of course, is available using names as well. So if you're using names, you just pass a dictionary in here. Oops, dictionary in here. And this allows you to apply a single value on each. So I could do 1:, that would be the same thing, or I could use, as I promised, the name, which is, no, I want to sum over W, sorry. Actually, I need to check and see what the name is. Capital W. So capital W. Capital W. There we go. And I could use the profile. So you can say h.profile. I can again give the integer or the name. Pretty much everywhere you can give the integer or the name. So I can give it I can profile out S, that will give me W, and I can profile out W, and that will give me S. So it behaves a lot like this thing. If you have multiple dimensions, you always give it the dimension you want to remove to make the, not profile, I don't know what I'm doing. Sorry. Profile will give you an actual profile histogram. So these are means across this, which is really nice. But what I actually wanted to do was project. And then I project the S-axis out, and that gives me S. There we go. That's what I was expecting. So you can project as many as you want here, and it will do that in this order. This is actually a good way to swap the axes as well, because you can't do that in UHI, but in indexing UHI. But you can do that with project. Okay, let's just do one. Let's pick another example to do. Oops. 3D histogram. All right, let's take a look at the density. So you can just call dot density, and that will get a density. Currently, just a direct array. But that's a quick way to get the density. You could actually compute that yourself fairly easily as well. Those are some UHI examples. Let me check the questions again. All right, we have a few that are multiple voted, so let's answer those. So about well, I think the statistics improvements will help there for the support for non-standard errors, but I'll get back. I'll get back on that one. I think we should be able to do anything root can do. So will Hist keep track of the X values for accurate interpolation? If you use the right type of histogram beforehand, yes. And any plans for a stack protocol in that? Possibly. I've thought about that. Since we now have a stack object, we might add a stack protocol as well. That would be nice for these things. Right now, it's really just a list of plottable histograms. So that's the sort of the current protocol, but it would be nice to formalize that. All right. Any more questions? Okay. Okay, let's just look at one more example. So we saw some plotting. Let's take a look at the different types of storage. So okay, so here's some different storages. So we can pass in an integer storage. So this is an integer storage choice. There's 7 different storage choices, and that produces actual integers from these things instead of the doubles you saw before. It's not particularly faster than doubles, and doubles cover pretty much anything you would want to do, and you can scale and stuff doubles a little bit more nicely, and fill with weights. But you can do actual integers if you'd like. There's a double storage, which is the sort of the default. Um,
I mean, I don't see anything in the source.
and you can, and the double, this thing that you end with is actually the storage name when you do the quick constructor. So let's take a look at a weighted storage. So I'm just going to try switching this to .plot.
You already flushed it? So you flushed it already?
And
Well, you don't need to flush now. It's fine.
let's fill this with a weight. So weight equals show. So you'll notice the plot of errors went away because it can't track these through this anymore. If I switch this to a double storage, it still can't track through that. And but if I switch to a weighted storage, it can. So this will store extra information to track these errors, and now it can go through this transformation because it's storing more inside the histogram. All right. I think that's you can also do mean storages here, which will then take a sample and it will do basically the same thing as a T profile. Okay, let's go ahead and end with this final question because then our time will be out. What does underflow, overflow, and flow represent here refer to? So similar to root, by default, boost histogram and hist keep track of anything that misses above and below. Actually, we pointed that out, I think, in this one. We just kind of breezed over it. But it's actually, even though when I filled this, I definitely, well, I should actually fill this one. Some of these actually do fall outside this range, especially right here. You see there's definitely some things in the overflow bin. So if I look at this H dot, well, hist overflow, you'll see that there are actually some entries in this overflow bin. Right, let's see if there's any in the underflow bin. There's a few in the underflow bin as well. So it keeps track of those, and that keeps track of all of these. And if you're integrating over, so if you're doing a two-dimensional histogram, and then you're summing over everything, it will include those flow bins. So you'll get exactly the same histogram out that you would have gotten if you had just originally made a histogram over that one dimension. So there's no harm in adding extra dimensions when you have flow bins. You can put explicit endpoints to turn off those flow bins if you do want to actually integrate over a fixed range. All right, I think that's all we have time for. So there's lots of extra examples here to feel free to look through. And we'll try to answer any of the remaining questions on Slack.